you'll be on the recording. I'm just going to wait until it says it's recording. It takes a minute to get ready to record. Let me. Okay. Guess that means we're recording now. I think I'll probably want to show you. Oh, it's not going to work, is it? Okay. I might not be able to show you. Maybe I'll just have to tell you about it. Okay. So, 10.1. Chapter 10 is on linear correlations. And so in 10.1, we're going to talk about how to determine if two variables are related linearly. And then in 10.2, we're going to talk about how to determine the nature of that linear relationship. So these sections are very, very closely related. They both use the same function on the TI-84, which is really the primary way we're going to do these problems. So 10.1 is on correlation. So a correlation exists between two variables when the values of one are somehow associated with the values of the other in some way. There's some connection between them so that when the value of one variable changes, it's going to cause the value of the other variable to change in maybe some semi-predictable manner. It might not be perfect. It might not be a perfect relationship that works a very specific way every time, but there's some connection where one's affecting the other. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. Now, in the real world, we don't generally get perfectly straight lines with our data sets. So we're going to have to be a little bit, flexible on what we accept as a general linear relationship. So the points should trend along a band of some kind. So the way I really like to describe it is when there's a linear correlation, the points will kind of follow along some kind of straight band when you graph the points. So it won't be an exactly straight line, but there'll be some narrow band within which the points all fit. And that would indicate that there's a linear correlation. All right, I'm sure I have an example here soon. So the requirements of a linear correlation. The sample of paired data. Now, in order to talk about a linear relationship between two variables, you're going to have two data sets. A data set for the x variable, a data set for the y variable. And they're going to be paired together, right? The x value of one pairs with the y value of how do I want to say that? So like the first x value has to pair with the first y value. They have to be related in some way or measured in some way that they're connected. The sample of paired data is a simple random sample of quantitative data, so it has to be numbers, not qualitative. Visual examination of the scatter plot must confirm that the points approximate a straight line pattern. You should check on that because sometimes the math can be fooled, where the math seems to point to a linear relationship, but then when you look at the points, you can tell there really isn't one. So you want to kind of confirm that when you plot the points, there is a straight line pattern occurring there. And again, it doesn't have to line up perfectly on a straight line, but if it's on some kind of narrow band, that would be good enough. The outliers must be removed if they are known to be errors, which I think you would want to do in every case, right? If you know you have errors in your measurements, you should remove those. The effects of any other outliers that are not errors should be considered by calculating R without the outliers included. Now, I apologize because we're referring to something that we haven't yet introduced here, but R is the measure by which we will determine if a relationship appears to be linear or not. So it's a number that we're going to calculate that's going to give us an idea of how linear the relationship is. All right. Any questions? No? Okay. So here's some examples. All right. So this scatter plot here, A, again, the points don't line up on a perfectly straight line, but they do seem to follow along a narrow band here. So I can kind of corral the points between these two lines. And that's the trend for these all these points, is that they all seem to follow along this band. And that band is a straight path, if you will. So this is a pretty strong linear correlation. Again, there's some variation in the data values. They do kind of jump around, but they can be corralled into this narrow band here. And so that's kind of what you're looking for a linear relationship. Contrast that with C, where the points are just like randomly scattered about the entire square, right? The entire rectangle. I shouldn't have called it a square, it's obviously a rectangle. So you can't really corral these points along some kind of narrow band. So this C has no correlation at all. In fact, the value for R here is stated to be 0. It's about as random as you can make it. So there's no linear relationship there at all. B, also, the points follow along a narrow band. But they're heading down as you go to the right, whereas for A, they're heading up as you go to the right. And so we would say, if they're heading up as you go to the right, that there's a positive correlation. That as X increases, Y also seems to increase. If they're heading down as you go to the right, as X is increasing, the values for Y seem to be decreasing. So that would be a negative correlation. When X goes up, Y is going down. Right? And then for D, you can see these points do not have a linear correlation, because again, there's not a straight path that we can use to corral these points between. There's no way for me to, I can't even really do it, where you try to draw a narrow band that holds all these points. There isn't one. So it's not a linear correlation, but there is a definite pattern with these points. And so it would be a correlation, but not a linear one. So this would be like a parabolic correlation, if you will, or quadratic, which we won't be worrying about in chapter 10. So we would say this is not a linear correlation, but there does appear to be some correlation here. There's some relationship between the X and Y variables, but it's not linear. And it's not something we're really going to be dealing with in chapter 10. All right, so to calculate the linear correlation coefficient, here is the formula to do this. It took me quite a while to actually construct this entire formula. It's very complicated, which is why I would recommend not, there's been a lot of things that have been complicated in this course that we have practiced calculating by hand, the hypothesis testing, confidence intervals. But this is one where I kind of draw the line. I'm like, that's just a lot of computation. Let's just have our calculator do it for us. So on the TI-84, the function that will calculate not only R, but a lot of other useful things, is the Linreg t-test. So I don't know, you might want to check your calculator to see if you have it on there. The Linreg t-test is not found under distributions, like the normal CDF, all that other stuff that we've been doing lately. It's found under test. So if you go to stat on your TI-84, again, I'm not going to be able to show you on the document camera because it's in use right now by the software that we have running. And then you slide over to test, the test menu. So you go right twice, and you'll see this list of tests. And it's kind of near the bottom, if I remember correctly. So scroll down, way down, yep. So for me, it's option number F. I know it might be a little bit different for you, but it's really far down to the bottom. So, and you'll see Linreg t-test there. And then when you select it, you'll get a menu, and it's going to ask you, where are your list of X coordinates? And you have to let it know which list to use. We haven't typed any data in yet, so we can't quite do this yet. And then, where's your list of Y coordinates? Tell it what list to use for the Y coordinates. And then frequency, just leave that at 1. It asks you if you want not equals to 0, less than 0, or greater than 0. You always want to leave that at not equals to 0. So if it's highlighting something else, you want to switch it back to not equals 0. And this has to do with the hypothesis testing, actually. So this is your alternative hypothesis for testing a claim about whether the relationship is linear between X and Y. And then you'll go down to calculate. So we'll do this in just a minute as soon as we have some data. But that will find R for you, so you won't have to calculate it yourself. So please use that instead of manually calculating this. All right. Here are the properties of the linear correlation coefficient R. R will always be between -1 and +1. It can equal -1 and it can equal +1. The closer R is to 1, the more linear the relationship is. And in fact, if R exactly equals 1, it's perfectly linear. It's a perfectly straight line. All the points are exactly on a straight line. Or if it equals -1, it's a perfectly straight line, except it's heading down as it goes to the right. If all values of either variable are converted to a different scale, the value of R does not change. So that's a really interesting property. So if your X variable was feet, and you decided to change it to yards, that doesn't affect the value of R. You'd still get the same value of R either way. Even though the numbers would change, since it's being changed by the same scale, the value of R would not be affected. The value of R is not affected by the choice of X and Y. So it doesn't matter which one's X and which one's Y. R will equal the same value either way. R measures the strength of a linear relationship. So as I mentioned, the closer it is to -1 and 1, the more linear it is. The closer it is to 0, the less linear it is. Where 0 is a completely random set of points that has no linearity to it whatsoever. R is very sensitive to outliers. They can dramatically affect its value, so we have to be careful about outliers. Remember, which are points that are really far away from the rest of the points. And as I already mentioned a couple times, closer R is to 1 or -1, the more linear it is. All right, so let's practice using the Lin-Rake t-test, calculating R, and then using that to determine if we have a linear relationship between these two variables, if there seems to be any linearity to it whatsoever. So what we have here is paired data for shoe length and height from 5 males given in this table. So again, they're paired. So these are for the same person. So the first person, their shoe print is 29.7 centimeters, and they are 175.3 centimeters tall. Right? It's the same person. The second person, also 29.7 centimeters for the shoe print, but that person is 177.8 centimeters tall. Right? But it's, again, same person. So there's 5 people here. It's a pretty small data set. Thankfully, it's less work for us to have to, do the calculations. So what we need to do is input this data set into our calculator using the list. We will put the X coordinates in one list. Right? So let's have X be the shoe print size. So we want to put these values into one list. You can use whichever list you want. I will go ahead and use list 1. And then we'll put the height as we'll let that be our Y variable. And we'll put these numbers in list number 2 in the same order. So these are paired. So if 31.4 is going to be the third value in list 1, then 185.4 has to be the third value in list 2 so that they get linked together. So you can't scramble the order of these numbers when you're typing them into the list. You want to follow the same order for both of them. So let's go ahead and type that in. So I'm going to clear out my list first because I'm pretty sure I have things there. So clear list number 1, clear list number 2. Go to stat, edit. That gives you your list. We haven't used list in a while, so I'm sorry if you guys forgot how to do that. And so I'm going to go do the X coordinates first in list number 1. So I have 29.7, 29.7 again, 31.4, 31.8, and 27.6. For list number 2, I'll have 175.3, 177.8, 185.4, 175.3, and 172.7. Was everybody good on? Can you do 2 lists on that calculator, or does it only has 1 list? Oh no, so I don't know if there's a way you can, if it would be able to do this particular function. So again, I can maybe let you borrow this calculator. Gregory,
I have 2 lists.
You have 2 lists?
Yeah.
Okay. Are you using the TI Inspire, or do you have a different calculator?
I think so.
Is it the calculator I gave you earlier?
Oh,
No, it's a different one.
can see if this one had it.
Okay, all right, no problem. Were you able to get the numbers in on your list? Okay. All right, so then you go back to stat, go over to test where we saw Lin-Rig t-test earlier. Make sure for your X list that it's referring to the list where you put your X coordinates. So for me, it's list number 1, which is the default name there, but if you need to change it, you could always do second and choose a different name, L2, L3, L4, whatever. For Y list, make sure it has the name of the list that holds your Y coordinates. For me, it's list number 2, which is the default name that's already there. Make sure, now that symbol next to the not equals to, 0, it looks like a P, but it's actually a rho. It's a Greek letter. So just like we see for like standard deviation and for mean, right? The population mean is mu, the sample mean is X bar. The population standard deviation is sigma, the sample standard deviation is S. So it's pretty common to use a Greek letter for the population and an English letter for the sample. And that's what they're doing here. So rho is the Greek letter R. It's the Greek letter for the population linear correlation coefficient. And then R, the English letter R, is the sample linear correlation coefficient. So what you're testing here is whether rho is equal to 0 or not equal to 0. Right? If it's not 0, there's some linearity to it. If it's equal to 0, then it's completely not linear. Right? So you want rho not equal 0. The reg EQ, I'm not even sure what that is, so skip past that, just leave it blank, just go to calculate. And you'll get this menu of results, and you'll see that R is actually not at the top there, on the TI-84 anyways. So you scroll down, and at the very bottom, you'll see R squared, and then you'll see R. So what you should get from your calculator, keep looking for my pen to write with there. For my recording, I don't want to use the pen because it's very loud when it hits the TV screen. So 0.5913. I'll just go 4 decimal places. All right, and so that's the value of the linear correlation coefficient. You get the same thing, Miguel? Yeah, okay. Were you able to get it to work on your calculator?
Nah.
No, okay. You might have to try to inspire. Well, if you want, I had a calculator that I thought another student was going to use who was learning from home. I left it at the math lab. Maybe when we take a break, I'll go over there and see, because I asked her, like, so have you been using that calculator just recently? She's like, no, I never picked it up. She just went and bought one on her own. So, of her own, I should say. So I should have another one of these. So maybe I could let, Jason, I could let you borrow this one and I could go get the other one from the math lab. Because these are just easier to use.
Yeah.
To inspire.
This one's kind of.
Yeah, it's really hard to use. I agree. It works, but it's just difficult. So, and it's difficult for me to teach when, there's 3 different calculators in use. All right, so any questions on how to get the value of R? All right, so here's a scatter plot of the data. Again, there's only 5 data points, so it's kind of hard to get a sense of the actual trend for these 2 variables, but it's, let's use a different color here. There is sort of a band here, and you might even say this bottom point down here to the right, it's a little bit of an outlier relative to the other 4, but there's still a little bit of a narrow band here that these 5 points kind of can be contained within. And so it's not the best linear pattern, but it's not the worst either. Same thing with R, right? This is about 0.6, right? So again, if it's closer to 1, it's strongly linear. If it's closer to 0, it's not linear at all. And this is somewhere in between, right? So it's really kind of hard to tell. Like that value of R is not really clear cut. It's kind of like halfway. And the scatter plot's kind of halfway, right? It's like, with these 5 points, it's really hard to tell like how linear that is. So we need a way of using the calculation you just did to decide if it's good enough to be considered a linear relationship. So find the critical value. So one way of interpreting R is to find the critical values and compare them to R. There's a chart for this at think Sylvia gave you that packet, and in that packet you would see a chart for these values of R. We can maybe try to look it up here on Google or something, because I don't have a chart handy. If the absolute value of R, so again, dropping the negative sign, that's all that's saying. Drop the negative sign. If the value of R you got is greater than the critical value, conclude that there is a linear relationship. If R is less than the critical value, then it's not linear. It's not strong enough to be considered a linear relationship. Now, the critical value you get for R depends on the alpha that you choose. And a lot of these problems don't actually give you an alpha, but it shouldn't matter. And there is a possibility that for alpha equals 0.01, you would conclude that it's not linear, but for alpha equals 0.05, you do conclude that it is linear. But I think these problems are going to be carefully constructed where it doesn't matter which alpha you actually choose, you should get the same conclusion either way. And so these will be listed in the chart. I was going to say, well, they have the test statistic on here, but yeah, they don't have the critical values. You can also interpret it by finding the p-value, which actually is given by the Lin-Reg t-test. The p-value is up here. So if you scroll back up to the top, you have p equals 0.2936. You can use a p-value. Again, compared to an alpha. And like I said, a lot of these problems don't provide a value for alpha, but what's typical would be 0.01 or 0.05. And this p-value is way bigger than any typical alpha value. So if the p-value is less than or equal to the significance level alpha, conclude that there is a linear relationship. Otherwise, if the p-value is greater than alpha, you conclude there's not sufficient evidence to support the conclusion of a linear correlation. All right. So for this particular problem, from the Lin-Reg t-test, we have a p-value of 0.2936. We'll go 37 if we round it properly, right? So this is the p-value. So it's just listed as p in the Lin-Reg t-test results. This p-value, if you compare it to an alpha, which again wasn't provided to us, but a typical value for alpha would be 0.01 or 0.05 would be like the biggest alpha that you would really consider using. Here, the p-value is greater than that value of alpha, which means this does not appear to be a linear relationship. I mean, the proper conclusion is there's not sufficient evidence to support the claim that this is a linear relationship. But paraphrasing, just doesn't seem linear. Okay. If p-value is less than alpha, then you would conclude that it does appear to be a linear relationship. Any questions on deciding whether it's linear or not? You get the value of R. While you're at it with the Lin-Reg t-test, you get the p-value. Use that to determine if there's a linear relationship or not. All right. You can also use the test statistic, which is also given by the Lin-Reg t-test. So for this problem, right above the p-value, it gives us the test statistic, which is 1.2698. I guess that rounds up to 9. I'm not doing a good job of rounding here. So this would be the test statistic for the data that we just had. Again, it's kind of a low one. But you could also calculate it this way by using R. But again, let's just use the Lin-Reg t-test. We're already using it to find R. So if you're using the Lin-Reg t-test to find R, you already have the test statistic, so you shouldn't need to use this formula. But I just wanted to show you what the formula was. Okay, and again, the p-value, you can use this number to find the p-value, but the p-value is given to you by Lin-Reg t-test also. All right. Now what you could do is you could find the critical value for t. So the chart that I'm talking about has the critical values in terms of R. But you can also find the critical value in terms of t by, again, selecting an alpha, which, again, let's say 0.01. It's always a two-tailed test for this, for the linear correlation stuff. So alpha divided by 2 would be 0.005. Right. Then you would do inverse t to find the critical value for the t score. The area to the left is 0.005. Again, the degree of freedom is n-2. Well, for our data set, we had 5 points, right? So 2 less than that would be 3. And so that should give us a critical value to compare to this, right? So I go to inverse t, 0.005, degree of freedom 3, I get critical value of 5.84. It's a pretty big value, I guess because the degree of freedom is so small. And so this would be the critical value, t sub alpha divided by 2. And again, you would draw a picture, and it's positive and negative, right? You have both positive and negative critical values in this case, because it's a two-tail situation. And so 5.8, whatever, that's where we're drawing the line. If it crosses the line further into the right tail, then we would conclude that it's linear. But if it stays in between these two critical values, it's not linear. Try that again, not linear. And that's what this one does, right? Because the test statistic is 1.2, whatever. It's in between the critical values, so we conclude that it's not a linear relationship. That'd be another way you can test it. All right. Interpreting the value of r squared is the proportion of the variation in y that is explained by the linear relationship between x and y. So r squared is also given in the Lin-Rig t-test, which I already lost the data for. So r squared in this case is 0.3496. Which is about 35% if you convert it to a percent. So we could say for this particular data set that 35% of the variation in y can be explained by the fact that there's a linear relationship between x and y. And then 65% of the variation is not explained by this linear relationship, which is why we're concluding it's not very linear, right? It's not really a linear relationship because such a small proportion of it can really be explained by that connection. So really most of that variation is due to something else. Now, maybe it turns out to be linear if we get more data points. The biggest issue with this one is that there was only 5 data points. All right, which makes a really high bar for determining that it's linear. If we had 40 data points, then an R value of 0.6 actually is pretty good for 40 data points. But for only 5, it needs to be better than that. Okay. Be careful when we talk about correlation. That means there is a relationship between the variables where if one goes up, the other one seems to go up, but it doesn't mean one is causing the other. So we talked about this at the beginning of the course. Causation versus correlation, right? So don't assume that the x value causes the y value to increase. We're just saying there's a relationship between the two. When one goes up, the other one tends to go up, but it's not one causing the other to go up. So it's wrong to conclude that correlation implies causation. Averages suppress individual variation and may inflate the correlation coefficient. So you don't want to use averages in your data set. Linearity, there may be some relationship between x and y even when there is not a linear correlation. So we talked about that earlier with that parabola graph, right? There's a correlation there. There's a relationship, but it's just not linear. So in this section, we're only testing for linearity, not for other kinds of relationships. All right, so let's try to determine if there's a linear relationship between these. So listed below are the number of times a cricket chirps in 1 minute and the corresponding temperatures in Fahrenheit. Is there sufficient evidence to conclude that there is a linear correlation between the number of chirps in 1 minute and the temperature? So the first thing we'll have to do is take this data set and type it into our list. So let's do that again. So we'll go to clear out list number 1. And clear out list number 2. And then we'll go to edit. In list 1, again, I'll let this be my x variable, the first row. So I'm going to list all these numbers and list number 1. All right. So we'll go in order that they're given. So 882, 1188. Do you want to, if you could go ahead and do that one? So you'll just do the rest of these. Just make sure you go in the same order. You just type the number, hit in, and hit enter. It goes to the next entry. And while you guys are doing that, Gregory, I'll go see if that other calculator is available. That way you can also participate. All right, I'll be right back.
Never do that. Someone crosses again.
For real.
It's too fast.
There's like some people, bro, it's like 5.
I know. I think I messed up.
I should do it online. And me?
Oh. Yeah.
Not there. You can always copy it, bro. Everything on the side.
Yeah, sure. Don't pass it.
No?
Don't pass it. If you don't see you can use also shit. Just take what you can. Instead of taking management finance, I'm not able to. Just take stats. And I already know basically I understand it at least.
But it's not the same as this, though.
It's-
It's not, bro. Oh, they're using Excel, bro.
Yeah, but the concept is because in Excel you
But
do
yeah, I
type
can
in
remember
a
about the concept, bro.
But
All right, here you go.
Thank
Thank you.
Yep. Yeah, that one.
Yeah. Yeah, I don't know why, who bought these or why or what purpose, but
Mr. Vaughn,
yes,
I think I messed it up.
what happened?
It's the window, I don't know. It's like shade rest or whatever. I don't know. It's just, that's I figured out, I think.
Oh,
Oh,
quit it, get out of that mode, I don't know what that's about, shouldn't be an issue. All right, so you want to go to lists, you might need to clear out list 1 and list 2. All right, so I don't have a calculator now, so I'm going to rely on you guys to help me with the results here. So once you get, and then, I'm sorry, I guess I didn't get that far, but then the second row will be our y variable. Use a different color here, y. And again, if it was me, I would put that as list 2. And once you have, and again, you have to go the same order that the numbers are given in, that way the data stays paired together appropriately. Then you're going to do linear t-test, which by the way stands for linear regression t-distribution test, right? And once you run that with list 1 and list 2, you scroll down to the value of r, and you find what is r equal to this time?
0.8737.
7, okay. 4 decimal places sounds good. Do the same thing, Jason?
Which button do I press to test it?
All right, you go to stat, which is where you do your list also. You get to it, or? No, see, you'll go to the stat button right there. Same place you went to do the list, yeah, right there. Then hit the right arrow to go over to the test. And then another, a little bit of a trick is you can just go up and it'll take you to the bottom. It'll be quicker that way. But,
And
yeah, another t-test.
then just test first. First, and then you do that. I don't think so. Yeah, it's just
that what you got? Okay, great, perfect.
List T, man.
Oh, that's this too? There's this one.
I have no idea.
Yeah, now, there was one calculator where it got deleted out, and I don't know if you do factory reset, it might like put it back, but,
Yeah, there's no this.
yeah, and then, so yeah, I think that calculator maybe has only like 3 lists available, so it's enough to do what you gotta do, but you won't be able to keep anything for very long, so.
List T.
So that's again.
Oh,
And just do
one, oh,
Got it? I mean, are you sure you know what to do?
yo,
All right.
again. Well, this two and this two. You got that?
All right. And just to show you guys what that chart looks like, well, that's not the one I'm used to seeing. Oh, it's really old too. Let's see. Alpha. That's table R. Oh yeah, but it's for correlation coefficients. So I guess that's an R right there. I don't know. I don't know what that is. 1, 2, 3. Degree of freedom. That must be the degree of freedom. All right. I don't know. Let's see if we can find a better one here. Okay. Yeah. So this kind of looks like what you would have, except the chart in our textbook only has 2 columns. It only has like 0.05 and 0.01 for alpha. But this way, you wouldn't have to look at the t distribution or t values or p values. You just get your value for r, which for us was 0.8, whatever it was. Then you find your degree of freedom, which is n minus 2. Now, how many data points do we have in our list? How many numbers do we type in?
Important. This one, this one.
Well, like how many x coordinates were there? How many numbers did we type in for x or for y?
8.
There's 8. So our degree of freedom would be 6, right? So the degree of freedom is 2 less than the number of data points you have, so it would be 6. And then again, you have to pick a significance level. But I think either one, now these would be the 2 that are in our textbook, 0.05, 0.01. But either one, I think our value for r is greater than that, right? We have 0.87. Right? So whichever one we might pick, our value for r will be greater than the critical value, in which case it is a linear relationship. Our conclusion would be this relationship appears to be linear. Right, so that's how you would use the critical value chart that's provided by the textbook, which you would see on my stat lab as well. That'd be one way to draw that conclusion. Right? The other way to draw the conclusion would be, so you compare this to the critical R values, which we get for degree of freedom 6. The chart tells us it was 0.737 was one of them. If alpha was 0.05, and then what was it for the other one? I was wrong about that. 707, 834. 0.834 if alpha is 0.01. But either way, this value of R is greater than the critical values. And so we would conclude that it's linear. All right. I'm sorry, let me change that. It's 0.707. Wasn't it? 707, right? Okay. 707. All right. So we conclude this linear. The other way you could draw this conclusion is to look at the p-value. Probably the easiest way, since you already have it on the limerick t-test. So why don't you guys tell me from the limerick t-test, what does it say the p-value is? It's on the same menu, but it's up near the top.
.0045.
0.0045. Right. So here, the p-value, again, we're not given a value of alpha in this problem, but whether you choose the usual, the usual ones that you might see are 0.01 or 0.05, whichever one you're picking for alpha, this will be less than those typical values, right? If the p-value is less, you conclude that there is a linear relationship between the variables. Right. So we would say, yes, there appears to be a linear relationship. That's probably the easiest way. Again, the other way you could do that is to take, the test statistic, which is also given there. Oh, well, I guess that gives you the p-value too. You can take alpha, calculate a critical value for the t-value, the t-score, compare that to the test statistic. But again, p-value is probably going to be the easiest way for you to make the determination. All right. So what is the null and the alternative hypothesis in this case? So for every linear regression problem, it's not regression, for every linear correlation, we're going to do regression in the next section. For every linear correlation problem, the null hypothesis is that rho equals 0, and the alternative is that rho does not equal 0. So if they ask you this on MyStatLab, every problem in 10.1, that should be your hypothesis. All right. Well, construct a scatter plot. I think let's just skip that. We won't bother with that. Find the value of the linear correlation coefficient R. You guys already did this with the Lindrig t-test. Find the p-value. We already did that. Find the critical values of R using a significance level of 0.05. That's what we did with the chart. It was 0.707. So if on the homework they ask for the critical values, which also I should say, by the way, it should be positive or negative because it's a two-tailed test. So positive or negative 0.707. Since it's plural, I would assume they want both of those. On MyStatLab, you should have access to that chart on that problem. There should be some way to click to open it up to view that chart. But you can also do a quick Google search like I did. Just search for critical values for R, and you'll find plenty of examples, plenty of charts. They should all agree on the critical value, so you shouldn't get different answers from different charts. And if it ends up being a problem, please just email me. Like if on the homework it's become an issue, you can't find the critical values for some reason, let me know and I'll help you out. Determine whether there is sufficient evidence to support the claim of a linear correlation. Yes, there is sufficient evidence because the p-value is less than alpha. So the answer here is yes, there is sufficient evidence. What percent of the variation can be explained by linear correlation? I'm not sure if that's on the homework, but if it is, it's just the value of R squared. So could you guys tell me what R squared was equal to from the Lindrig t-test? 0.76. All right, so that'd be 76. And again, I don't know how far we should round it, but if it's 0.76, that's 76%. So 76% of the variation can be explained by the linear relationship. And what is that? 24%, the variation is due to some other factor, something else. Right. Any questions on linear correlations? All right, looks like this was our last example. So why don't we go ahead and take a break for about 10 minutes, and then we will look at 10.2, which I think will be even, I think it'll be quicker, but I don't know, this is the first time I'm running through these notes, so maybe it'll be the same amount of time. We'll find out though. All right, so let's go ahead and take a break. I'll go ahead and pause the recording. Well, the other thing I kind of wanted to do is to make this part of the recording, let me this tools. I wonder what that's going to look like in the video. All right. Wanted to snap a picture. Uh-oh, I messed up. Let's do this first. And this. Where's it at? That's down here. Okay. That way this becomes part of the video. All right, new page. Okay, and so this is how we got the critical value. The degree of freedom was 6. Alpha was 0.05, according to the second page.
But even if it was 0.01, either way, we're drawing the same conclusion, but this is how we got the critical value from this chart. Okay, so let's stop the recording.